Hi, class. Welcome to chapter 13.6. Today we're going to talk about absolute convergence. So let's go through a definition. So if we have a series, A sub n is called absolutely convergent if the series of absolute values of the formula for the sequences is convergent. Okay, so what does this look like? So a series is called conditionally convergent if it is convergent but not absolutely convergent. Okay, so there's a difference between absolutely converging and conditionally converging. So let's look at an example that kind of shows us this, right? So let's consider the series um, -1 to the n minus 1 over n. So if we look at this, this is basically the alternating harmonic series, right? We have 1 over n, and that 1 over n is changing signs for each term, okay? So this is the alternating harmonic series. So the first condition that we had from the previous section, um, we are doing the test for convergence for alternating series. The first condition was that every new term is less in value than the previous term, and we know that that's true for the. So as we look forward, we know that each new term is less than the previous, and also the limit of just the formula, 1 over n, we know that that goes to 0. So the alternating series of the harmonic series is convergent, okay? But we know that the harmonic series itself, when it does not alternate, is divergent. So the harmonic series is conditionally convergent, okay? Or I should say that the alternating harmonic series is conditionally convergent, okay? So the alternating harmonic series is conditionally convergent, right? So the absolute value of the alternating harmonic series is the same as the harmonic series. Okay. So for our next term, if the series A sub n is absolutely convergent, then it's convergent, right? So um, the alternating harmonic series is convergent, even though it is not absolutely convergent. Absolute convergence means convergence. Okay. So this comes to what we call the ratio test. The ratio test is sort of a big test for us. It doesn't work all the time, but it works a lot of the time. It's my favorite test. It's the one that I use the most often. Although it's not always appropriate, it is the one that works the most. It works for me, right? And when it doesn't work, then I start to try to move towards other tests that may be appropriate. Okay, so for the ratio test, first condition is that if the limit as n goes to infinity of the absolute value of our formula for the sequences plus 1 for n divided by our sequence itself, formula for the sequence, um, goes to a limit L that's less than 1, then the series is absolutely convergent. Okay. If it is larger than 1, I believe is the next one, then it is divergent. Okay. So if it's larger than 1 or infinity, which obviously is larger than 1, then the series is divergent. And if the limit L is equal to 1, then our ratio test is inconclusive and there's nothing that we can say about our series. And then we would have to move on to some sort of other test for convergence. Okay, so I really like the ratio test because it's fairly easy to calculate and you can come up with an answer right away. Either it's absolutely convergent or it's divergent. Now, if you get something that is like the alternating harmonic series that is conditionally convergent, you're going to come up with a 1. Now, 1 does not mean conditionally convergent. A 1 means the test doesn't tell you anything. It can't tell you if it's convergent or divergent, and you would have to move on to something else. Okay. So no conclusion can be made about our series by using the ratio test. So I like using the ratio test because I get one quick calculation and then I can say convergent or not convergent. And then if it's equal to 1, then that's when I move on to more like of a specific type of test, depending on what my series looks like, right? I might do a comparison. I might do I might just check for a divergence by looking at the limit itself. Maybe I need to use an integral, et cetera, et cetera. We cover that in the next section about when to use which test, right? So let's look at an example of our ratio test in action. Okay, so let's determine the convergence with a ratio test. For the first one, we'll have 1.1 to the n divided by n squared. Now, as a mathematician dealing with a lot of numbers, I like to turn my decimals into fractions when it's easy to do, right? So this would be 11 over 10 would be the easiest way for me to look at this. However, we should be able to work with it as a decimal um, as well. So in this example, I just keep it as a decimal and I work with it. But for my own posterity, I like to change things into fraction form when it's easy to do, right? If this was like 1.23479, I wouldn't deal with it. I would just leave it as a decimal. But something like this, for me, 11 over 10 is easier to look at and to analyze. However, we're going to just keep it as it is. So we're going to take this thing, and everywhere we see n in the formula, we're just going to put n plus 1. So we have 1.1 to the n plus 1. I have n plus 1, that whole thing being squared. Okay, so remember, it's not n squared plus 1. The n is being squared, so that's why I put n plus 1, and then I square it. I divide that by the sequence itself as I see it, which is 1.1 to the n over n squared. And so the next thing I need to do in the limit is I'm not just going to go and calculate this limit as I see it. I'm going to obviously whittle it down. I'm going to do a little bit of algebra. So I'm going to flip this and uh, the denominator and multiply it. So I'll write it like this. Okay. As we continue to progress, you will see me skip this step and just write it like this. I do this so often that I know I flip this upside down. I take the reciprocal, right? And that's on the right side. And on the left side, I just write what I see here and just write plus 1 whenever I see an n, right? So it's a lot easier just to do this straight away than it is to go ahead and flip it this way. So here, there's always some cancellations that we get to do. Here we have 1.1 to the n plus 1. That cancels with this 1.1 to the n, right? This is the same base with different powers. And so when I cancel, when I have n plus 1 minus n, I'm left with just 1.1 in the numerator. This n squared and this n plus 1 squared, nothing cancels here, right? So I'm not going to cancel anything with this, but this 1.1 does, right? So what I'm left with is 1.1 n squared over n plus 1 squared. It is very clear that the denominator does not really grow any faster than the numerator. This is basically n squared over n squared. So the limit as n goes to infinity is just the ratio of their first terms. And so that first term here is just 1.1, right? So the limit is 1.1, which is larger than 1. And if we go back to our test says that if we are larger than 1, then the series is divergent. So by the ratio test, right, this limit is 1.1, which is larger than 1, which means that my series is divergent. Okay. So again, I like this test because generally things cancel out and I can tell if it's divergent or absolutely convergent pretty quickly. Again, if this came out with a result of 1, I'd have to apply a different test. Okay. So here we have n plus 2 over n times n factorial. So we're going to do the same thing. I'm going to write the limit where this is my numerator, where I'm adding 1 for all of my n's, and then I'm going to multiply by the reciprocal of this. Okay. So here I actually write it out for you guys. I'm being nice, right? So I have n plus 3 on top. This is n plus 1. And this is n plus 1 factorial. And then on the bottom, I have just my standard form, right? The n plus 2 over n times n factorial. Flip the reciprocal, or I'm sorry, multiply by the reciprocal of the denominator. Okay, and then we try to see what can cancel out. Now, for this n factorial, if you write out n plus 1 factorial, the next term is n plus 1 times n minus 1, etc., etc. So I could rewrite this as n plus 1 times n factorial. So those factorials cancel. Okay. So then what I'm left with then is I have this n that's still here with this n plus 3. Okay. I have this n plus 1 plus the n plus 1 that I pulled out. So I have n plus 1 squared. The factorials cancel. And then I have this n plus 2 left over. So looking at this, right, my numerator is an n squared as the highest power for this polynomial that gets multiplied out. If I were to expand this, the power would be an n squared and another n, so n cubed. So I have a polynomial on top, a polynomial on bottom. However, the denominator is a higher degree, which means that this grows faster than the numerator, so the limit goes to 0. Okay, so the limit here is 0. So remember what this says. If it's larger than 1, I'm divergent. If I'm less than 1, which is 0, then I am absolutely convergent, right? So this series converges absolutely. I know you can't see this n equals 1 on the bottom here. I apologize for that, but in the write-up, it will be visible. So don't worry about that. Okay. Next, we have the root test. The root test is very, very, very similar to the ratio test, except we use it when we have powers of n present. Okay, so if I take the limit as n goes to infinity by taking the nth root of the absolute value of my series, and that equals L, L here being less than 1, okay? Less than 1, I get the same output that I am absolutely convergent, okay? If I take the limit as n goes to infinity of the nth root of the absolute value of my formula for the sequence, for the terms for my series, okay? And that is larger than 1, then my series is divergent, okay? Just like with the root test. And if that limit comes out to being 1, then it's inconclusive, right? Again, the results here are just like the previous test, right? So let's do an example. So let's determine convergence by using the root test. Here we have 1 over n to the nth power. I can consider this as 1 to the nth power is 1 as well because it's always 1 in the numerator. So if I take this, the nth root, and I take n to infinity, calculating and simplifying this, I'm going to get 1 over n. Okay, and we know that this goes to 0, which is less than 1, which means that this series is absolutely convergent. For 2 to the n and over n squared, right? So whenever I see an nth power, that generally tells me this is a good time to use the root test. If you look back on the examples we had here, um, this one would have been a good example to use the root test as well, right? 1.1 to the n over n squared. Here we use the ratio test. So if you look at this example that we're doing here, it's very, very similar to that. Okay, instead of 1.1 to the n, it's 2 to the n. It's almost the exact same problem, right? So I can use the root test here, or I can also use the ratio test. Same thing here. I could use the ratio test here as well. Just 1 over n to the nth power. I think we didn't have that for this example. I think that was a previous video. Okay, so let's go through the work and take the nth root. So the n that's attached to the 2 cancels out. This turns into 2 divided by n. Well, when this n gets very, very large, this is going to go to the 0, okay? And this is going to get very, very large. So we kind of have a L'Hopital's rule problem here, right? We can do that work, but we know from the previous example that it's just the numerator that ends up staying, right? So just like for this previous one, the form was exactly the same, and our limit came out to just this 1.1, right? So it's going to do the same work. It's very easy to see here by doing the ratio test. Again, from what we have going on here, the method that we chose to do, we would need to use L'Hopital's rule in order to kind of see what happens here. And we're going to end up with 2, which is larger than 1, which means that my series is divergent. Okay. So the next thing that we're going to briefly touch on is the idea of rearrangements. If we have a series that is absolutely convergent, not partially convergent or conditionally convergent, but absolutely convergent, to a sum of s, then any rearrangement of our series is going to have the same sum of s. Okay, so if we mix and move things around, we're always going to come up with s. However, if we are conditionally convergent, then and r is a real number, then we can rearrange our series to equal r. Okay, so if we're absolutely convergent, it doesn't matter how we rearrange things, the sum is always the same. However, if we are conditionally convergent, we can rearrange our series to equal any value that we want, okay, as long as it's a real number, right? So conditional convergence is very, very interesting in that respect. Um, there are examples in other calculus textbooks. I didn't want to put one on here. It's a very, very interesting idea and topic. However, there's a lot that kind of goes into these rearrangements, so I didn't really want to sort of mess with it. But you can pretty much go anywhere to see this. In fact, let's take a quick tour of the internet. We'll do a quick exploration, but we'll do it the lazy way. So let's go ahead and just look at Wikipedia. So this is the Riemann series theorem, and so it states here that so this is also called the Riemann rearrangement theorem, and it basically says that if you have an infinite series of real numbers that is conditionally convergent, okay, then its terms can be arranged in a permutation, meaning you just move things around, so that the new series, oops, trying to be nice about this, the new series converges to an arbitrary real number. Okay, so and I can have it rearranged such that the new series diverges as well, which I didn't know. I actually just learned that right now. So if we take an example, they had a really good example for um, natural log, right? So I would go through this, or so they're giving you this example series. They don't tell you, it says it converges to zero, right? So I have one, I'm going to subtract one. That's nothing. I'll add a half, I'll subtract a half. That's nothing. I'll add a third, I'll subtract a third. That's nothing. So it's very clear that this converges to zero, okay? Now, if I move stuff around, okay, or I'm sorry, the absolute values are going to go to infinity because I'm just adding a bunch of large stuff here. It's like adding two harmonic series together, basically, when I take their absolute values, right? So this is going to diverge. So that means that it's conditionally convergent, right? If I take the absolute values and they don't converge, but the alternating series does, that's a conditional convergence. Now, if I were to rearrange things so that I have 1 plus a half, okay, so 1.5, and then minus 1, I'm at a half. And then I can add some values and subtract some. This is going to converge to natural log of 2, okay? So this is a very common example. I didn't want to write this all out because it's here available for us on the internet. But if we go through this, there's a couple of other examples, right? I'm not going to go through all of these, but here we have the series for natural log of 2. And the next, not the next uh, section, but the section after that, we talk about looking at functions as approximated by series. So we'll talk about this a little bit more a little bit later on. But for right now, that's the end of our video that we have. So I'll see you guys on the next section.